All right, fantastic. Welcome to Code Camp. It's so nice to be back here again. Before I get started, we will be doing a panel on AI around 3 o'clock. And we have a little bucket here. I bet you're wondering, what's this bucket doing on the stage? Well, what we decided to do is entertain questions from all of you in the audience. And so before lunch, I should say, if you have a question that you'd like us in the panel to address regarding AI, there's paper, pens up here. Just jot down your question, fold it up, put it inside the bucket right here, and we'll answer it at the panel. So fantastic. I want to talk to you today about 4 key trends towards better software architecture. And as a matter of fact, I'm going to talk about 4 of these. The first is architectural intersections. And the second is this but practice called architecture as code. The third trend I'm going to talk about in this keynote is the rise of distributed architectures. And finally, one of my favorite topics is AI-driven architecture. So let's dive right into the architectural intersections. And what do I mean by this kind of trend? Neil Ford and I, in our book, The Fundamentals of Software Architecture, created these star charts. We rated all of the different architectural styles based on various characteristics. Which architectures scale better? Which ones are more agile? Which ones are more responsive? And based on our needs, we look at the star ratings. We can do what's called qualitative analysis, and we can say, you know what? This architecture right here would be best for scalability. So we go and implement that, and it doesn't work. We read our second book, which was Architecture, the Hard Parts, which is all about trade-off analysis and how to make really hard decisions in distributed architectures. And you follow all of our guidelines, make all the right decisions, and your architecture still doesn't work. What's the problem with this? The problem is the fact that architecture does not live in a silo, but rather it has to be aligned with other aspects of the business and technical environment. We call these architectural intersections, where architecture intersects with these various aspects. As a matter of fact, my friend Neil Ford coined a term, architectural nexus. Now, nexus is an intersection. Nexus is plural for intersections. However, no one can pronounce that word. So we decided not to use it. These are known, though, as architectural nexus. Well, let's take a little journey through what I mean by these intersections and why they're so important in order to make architecture actually work. And that first intersection we're talking about here is that of architecture and implementation. The first one that pretty much is near and dear to architects and developers. If you take a look at this room right here that we're in, it has a particular architecture. There's measurements of load bearing for how much we can span on a particular beam or piece of wood. You know what we're hoping, everyone? We're hoping that this room was implemented to that architecture. And when I say implemented, all the contractors and workers and masons and carpenters and electricians all constructed this room to that architecture. How often do architects create lines and boxes, identify components and domains, the coupling between those, and present that to a development team? And the development team looks at that and says, oh yes, I see your vision. Thank you so much. Now go away and let us code. That would be pretty scary, wouldn't it? And it happens all too often. Architecture has to be aligned with implementation. The second alignment is that with architecture and infrastructure. Oh yes, we selected an architecture that can scale and is highly responsive. We align it with implementation, and so that we're not doing anything through coding practices that prevent or inhibit that particular responsiveness or scalability. Where's it deployed? What kind of virtual machines is it on? Where's the network? How many subnets am I going through to actually access my data? So we have to be aligned in architecture and infrastructure as well in order to make architecture work. The third intersection is that of architecture and data topologies, and also database types. I wish I had about 4 hours for this keynote, because I could spend about that much time talking about this rant that I'm trying to keep myself from doing. What I mean by database topology are monolithic databases. Should we break our database, our physical database, up into domains? Or even, in microservices, database per service. Does this impact the architecture? And the short answer is it does, as well as the type of database we use. And so consequently, data and architecture are not two separate things. These are not two separate activities. These must be aligned in order for architecture to work. Now, those are all the technology aspects kind of this alignment with architecture to make it work. But there's other ones as well involving process. For example, the intersection of architecture and engineering practices. We have a highly agile architecture. What about the processes and procedures and methods we use to actually develop software? Do those match the architectural concerns of agility and that ability to respond quickly for change? Or a highly testable architecture, but our engineering practices don't lend themselves towards testability. And so this alignment, although this one may seem strange, is equally as important for our architectures to work. Closely linked with engineering practices is the intersection of architecture and team topologies. And when I refer to team topologies, I'm really referring to maybe either the partitioning of a team, technically, or domain, or even the team topologies as described in the team topologies book. As a matter of fact, I'm going to show you some of these alignments in another one of the trends I'm going to show you. I did mention that architecture does not live alone. It's not in a silo. And so the next intersection is that of architecture and systems integration. If I need to communicate with another system, another third-party service, how does that impact my architecture? Am I communicating synchronously with those particular systems or services? What's the contract look like, the rate of change of contract? In other words, I'm not just an architecture or a system that can stand alone and not be influenced by other systems I'm integrating with. And so this is another intersection we have to pay attention to. The other one is the intersection of architecture and the business environment. It's kind of interesting when we talk about the business environment. Is your business undergoing severe cost-cutting measures? Or is it aggressively expanding? Do you have to focus on regulatory compliance? Do you have a complex business domain, or is it fairly simple? Are you a startup or a very well-established, mature company? All of these things impact the architecture. And when I talk about this kind of alignment or intersection, the type of architecture impacts these kind of business environment factors. Now, linked with the business environment is also the intersection of architecture and the enterprise. Are there practices, procedures, libraries that we have to use, standards in the enterprise? Are we incorporating those into our architecture? Because if this alignment is not met, it probably won't work within the enterprise itself. And the last one, which of course everybody is interested in, is the intersection of architecture and generative AI. Now, I'm going to touch on this a little bit towards the end of this keynote. But my friend Neil Ford is actually going to end the conference with a keynote based on this intersection right here. So you're going to get 45 minutes worth of detailed information about this kind of intersection, mostly involving the environment. Okay, the second key trend in architecture is this thing called architecture as code. Isn't it interesting? We have policy as code, we have infrastructure as code, and now we have architecture as code. What does this even mean? This trend is one of the fastest growing trends that I have been experiencing in the past 5 months. So the other premise is this: in order to make architecture work in our systems, it has to be governed and measured. I just talked about all these alignments, and we can measure structural, we can measure operational, and also we can measure process-related things to that architecture. As a matter of fact, I just showed you the first trend, and that's an understanding that as an architect, as a tech lead, as developers, we have to pay attention to all 9 of these alignments. Because if we don't, that's why architecture doesn't work. But how do we know if we're aligned? How do we verify that we're aligned? That's where architecture as code comes in. I'm going to show you what I mean by architecture as code, actual executable code that describes our architecture. But this trend is used to ensure alignment with all facets of the architecture. You know what the other better part of architecture as code is? How do you describe your architecture? Any kind of architecture. This building, our software, it's through diagrams. Yes, but diagrams are not executable. They describe our architecture, we can see the architecture, but we can't enforce those constraints and those principles through a diagram. Architecture as code allows us through software, through executable code, to be able to describe our architecture through a language. So we call this, Neil Ford and I created this architecture definition language, ADL. And as a matter of fact, if you're interested in it, you can go to my website at developer2architect.com. I believe it's in the bio. And go to the resources page, and you'll see it 3 resources down. This is a pseudo language that we can use an LLM to be able to generate structural tests, executable code, so that we can actually enforce that these walls have a certain characteristic to manage that load. I can also use operational tools like Datadog, or maybe it's Kubernetes combined with Prometheus, to be able to analyze a lot of the operational concerns, and also write my own fitness functions for process-related aspects as well. So we talked about these intersections. Let me show you a couple of examples of architecture as code. And as a matter of fact, let's look at one of the strongest forces here, which is the intersection of architecture and implementation. This is my architecture here, where I've defined some domains within my architecture. How do I know those are being enforced? I can write architecture as code, executable source code that describes my architecture. As a matter of fact, let's do that. These are the domains in our system. These are the ones we identified, either through domain-driven design or any other means. So here's my system. Now, SysOps Squad is a fictitious company. Actually, it's a real company, but it's a fictitious company that does trouble ticket management for electronic devices. We have tickets. So I'm going to define a domain ticketing as ticketing. I'm going to define a domain customer. And I'm going to define a domain survey. These are our 3 main surveys. And I can assert that all source code in our system falls within these domains and subdomains. And as a matter of fact, this is the association. What do I mean as ticketing? How does this actually work? Those domains that we identify are actually manifested through our namespaces or our directory structures. And so in other words, in a domain partitioned architecture, there's my system, sysops, for sysops squad. It's the highest level directory. And my domains then fall under this, whether it's a distributed architecture or whether it's a modular monolith. And I notice I have customer here, which matches to that directory structure or namespace, correspondingly all these other domains. What use is this? I mean, I've described my architecture. This is the use of it. Because I can leverage Gemini, ChatGPT, Copilot with a simple prompt to say, given this pseudocode, generate for me an ArcUnit test in Java. Generate for me an ArcUnit net test in C#. Generate a PyTest arc in Python or a TSArc test in JavaScript. And consequently, now we gain an understanding and saying, yes, this is what I'm interpreting that you're wanting to do, and here's your corresponding executable source code generated from that ADL. This describes my architecture. And consequently, I can now hook this into JUnit, or in the case of C# and Unit, I can hook this into our CI/CD pipeline. And now, if there's any code or any new domain that happens to appear, this test will actually fail. And so these are some examples of the intersection with implementation. But what about other aspects? What about the infrastructure? We can leverage architecture as code for this as well. And so the business says, of course, the order submit API call that we have must be able to scale to 5,000 concurrent users with an average response time of 600 milliseconds under load. That's our requirement, everyone. And the architect says, okay, no problem. Yeah, we can do that. 2 questions for all of you. First question, where is this information that is critical, that describes our architecture, documented? Where is it? It's probably in some document somewhere, but it's part of the description, the characteristics of that architecture. And my second question to all of you, how do we verify that we actually did this? And the answer is architecture as code. I can write an architecture definition language that describes my architecture from an infrastructure standpoint and basically say the following. Here's my system, com.order entry. I've got a max user load as 5,000. I've got another constant as 600 milliseconds. Assert that the response time is less than or equal to the average response time at max user load. Now, unfortunately, I can't put this through ChatGPT or Gemini or Copilot or any other LLM, but what I can do is now either write custom fitness functions to track this or leverage tools such as Datadog or Kubernetes to be able to track and verify this. I have right here at the top architecture definition. That defines our architecture. Where is that in our diagrams? It's not. It's in a decoupled document somewhere that no one knows where. And as a matter of fact, by doing this, either through tools or custom fitness functions we write, we can now start tracking this to ensure this alignment. Why is this critical? Things change, everyone, constantly. And not only business, but technology. How can I ensure that we're still scaling to these specifications? This is how. Because we notice as we start increasing our user load, we can calculate the slope of these data points. I can calculate the standard deviation of these data points and demonstrate to you that slope is 0. This defines a scalable system. Now, if that slope started to go up, if the standard deviation increases, we don't have a scalable system. We're no longer aligned with our infrastructure. Another interesting example is that of data. There are so many types of tests, fitness functions, that we can run to verify our data. And as a matter of fact, let's take a look at 3: data integrity, referential integrity, data consistency, and data loss. And so here's another interesting example. The architect says, yeah, I decided to split the database into 2 domains with very good justification for this. I get better fault tolerance, better maintainability, better change control, better scalability. It's a good justification. The business says, okay, great, we got it, but please, can you make sure that in one domain where you have tickets, we have other domain that has those same tickets and that we're not losing any data? Oh, yeah, sure, no problem. Because where is that documented? And how will we verify it? Architecture as code. Architecture definition languages, pseudocode that we can write that describes that constraint. And as a matter of fact, where is this kind of decision that you see here documented? Typically in an architecture decision record, an ADR. That's where it's documented, Mark. You know what? You're right. This is an architecture decision. How's it enforced? That's where we couple architecture decision records with the ADL, the architecture definition language. And I effectively now have a description of my architecture. Ticket data consistency check. Here's all of my domains, admin and ticket. Assert that tickets must be consistent between these domains. And I can actually write a custom fitness function. Executable software that ensures this alignment. And let me show you that software. So here's the scenario. I chose to break up my database into 2 domains, a customer domain and a ticketing domain. Customers enter tickets into our system, and then they're processed and assigned. Well, what I can do is this. I know the number of tickets in that database. That's a simple query. Select star, select count. I know how many tickets haven't been processed yet, because I can look at the queue. I know how many tickets have been processed. We'll call that D2. And I can assert and write code that continually runs in production that says each hour, check to see that D1 equals D2 plus S, which is the number of tickets in the queue. Sent. I was like, why did I call that S? It should be P for pending or something, S for sent. These were sent. They're still pending tickets. However, what about foreign key constraints? When we break apart a database, do we come misaligned with our data? We can also leverage this as well. Because I can do a hash of all the customers we have in our first database, in our customer domain. I can also get a hash of all the foreign keys for all those customers in the other database. And at some point where we're idle, let's say at 3 o'clock in the morning, I can now calculate and say, is H1 equal to H2? If it is, we're good. If it's not, we're not aligned anymore. Something's wrong. And now I have to investigate it. Let me show you one more example, and that's the team topologies. Wait a minute. You can use architecture as code to validate that we have the right kind of teams in place? The answer is yes, we can. As a matter of fact, let's go to Team Topologies book. The 4 basic kind of teams are stream-aligned, we have enabling teams, complicated subsystem, and platform teams. We choose to organize our team topology as follows. We've got an admin team, a team set up for all of the administrative stuff that happens in our system, and that's a stream-aligned team. We have a ticketing team. This stream-aligned team works on all the stuff involved with ticketing. But you know what's really complex? When we get a ticket and we have experts in the field, we have to find an expert and locate them. That is what's considered a complicated subsystem. Let's create a complicated subsystems team for that ticket assignment. Is this the right topology for our architecture? How do we determine this? Because one way to check is to say, are these teams getting in each other's way? Should it just be one team? Should we have 4 teams, 5 teams? How do we measure this? Architecture as code. An architecture definition language that basically specifies how can I determine if they're getting in the way? One metric we can use is merge conflicts. The more merge conflicts I start getting between teams means the more they're starting to touch each other's code, the more they're getting in each other's way. And so here is my specification. I can say this, define my teams, assert that merge conflicts between admin and ticketing subteams, or those streamlined teams, is less than 5%. Oh, we expect maybe a little bit because we're dealing with some shared code and objects and stuff like this, but make sure that's less than 5%. However, our complicated subsystem teams should help streamlined teams, not inhibit them. How can I tell? There should be 0 merge conflicts there. And between the fact that the complicated subsystem team is dealing with ticketing stuff, less than 10%. Now, I can generate code. Create for me code in GitHub that determines merge conflicts and measures them. And there it is right there. That's executable code that ensures that alignment. All right, wonderful stuff. So 2 more key trends. The third one is the rise of distributed architectures. We've known for a while that microservices is definitely a trend in the industry, but that's not what I'm talking about here. I'm talking about distributed architectures because there are other core distributed architecture styles, such as service-based architecture, event-driven, which is definitely back on the trend rise, and also space-based architecture that leverages caching instead of databases to get the highest levels of scalability, responsiveness, and elasticity. A lot of social media platforms are leveraged with this. But why is this a trend right now? It's a trend because of this. Constant change. Everyone, we are experiencing change in business, platforms, technology, deployment environments. Everything is changing. Back in my day, all these people with gray hair always say that. Back in my day, business has changed. But the rate of change to pivot a business usually took a year, sometimes more. Today, those pivots and changes based on market conditions and other things I won't mention, basically those pivots are in months of time. Folks, everyone, we in IT, architectures, have now become the bottleneck. We cannot change fast enough with the amount of technology change and business change we have. We need levels of modularity to be able to be more agile and partition and break apart our systems. We need better fault tolerance, so when failures do occur, we're not knocking out the entire system. We need better levels of scalability today because of the amount of mergers and acquisitions that are happening all across the world. And we need better ability for continuous deployment and integration. It's interesting. All these factors are the superpowers, not surprisingly, of distributed architectures. But this is only one half of the trend ingredient of why this is an increased trend. The other part is because of cloud deployments. Because with cloud deployments, we can now start realizing these things that we are struggling with or have been struggling with for years. Multi-region deployments that give us better performance, less latency, less redundancy. Coupled with that is edge computing, which gives us much better response time and less bandwidth. Everyone, these things are not possible without distributed architectures. Kevlin Penny is going to be giving a
fairly detailed talk on all the stuff about distributed architectures. But my last word for you is this on this topic. Proceed with caution. While we get excited about this trend, we have to be careful as well, because distributed architectures are hard to test. Distributed architectures cost a lot of money. And distributed architectures, trust me, I've written 3 books on them now, are complex. Proceed with caution. But this is a trend. We cannot avoid distributed architectures in our industry anymore. I am not saying, by the way, that monolithic systems are dead. Oh no, far from it. But the trend in our industry now is moving away from those where needed. One last trend I want to end this keynote with is with a very exciting trend called AI-driven architecture. How long have I been doing AI? 16 years. That's how long I've been involved in AI. What do you mean? It's only been around like a year. No, let's go back in time. Because while I was working at IBM, back in the late
2000s, we were working on something called autonomic systems. An autonomic system is a system that can be aware of itself, repair itself, and hide all those complexities from operators and users. Back in that day, we defined an autonomic system having 4 key properties. The first property, that system has to be self-aware. In other words, ability to monitor itself and assess its state. An autonomic system has to be able to be self-configuring, based on that self-awareness, to automatically change its configuration, are you ready? Without human intervention. Self-healing, the ability to automatically discover faults and repair them without human intervention. And the fourth property is self-protecting, to be able to be proactive in terms of attacks, learning from those attacks to prevent those in the future. What kind of system am I talking about? Well, I'm going to show you exactly an autonomic system, but let's have some fun first. I'm sure all of you, regardless of your age, have heard of 2001: A Space Odyssey by Arthur C. Clarke. And I'm guessing you remember the most famous character, Hal. Hal was the computer that ran the spaceship heading towards the monolith. Hal was an autonomic system. Hal was self-aware, self-configuring, self-healing, and self-protecting. Well, do any of you remember what ended up happening towards the end of that book or movie? Dave was locked outside of the spacecraft, and Dave said, "Hal, open the hatch." Does anybody remember the chilling quote from Hal? If not, you should see this movie. It's great. Hal said, "I'm sorry, Dave. I'm afraid I can't do that." Because he knew Dave was going to shut him down. Self-protecting. Hal was an autonomic system. When I talk about AI-driven architecture and autonomic systems, I can't help but refer to this book. This is one of my favorite books about autonomic systems and AI. This is a book called The Kraken Project by Douglas Preston. Now, in this book, we were sending basically a probe to one of Jupiter's moons, Titan, because we detected the possibility of life in one of its oceans. Can you imagine, can you guess as a developer right now, creating the software for that probe, for that ship? Can you imagine trying to guess at all the various conditions, scenarios that you would ever hit? No, it's not humanly possible. So the programmers basically developed Dorothy. They coded a core, put it in the spaceship. It was in this large building about this size that was a tank simulating the environment on Titan, Jupiter's moon. Dorothy was an AI that was able to learn, be self-aware, and self-configuring, write her own code because we could not predict and develop all of the possible scenarios. Well, you can guess what happened. There was a little mishap, and all of a sudden, disaster happened, and Dorothy said, we're going to explode. Now, Dorothy did not know, this AI, that she was not on Titan. So self-protecting, what did she do? She escaped the ship before the building blew up and went into the internet. That's how the book starts. I'll let you read this to see the adventure of Dorothy, an autonomic system from learning and self-configuring, self-protecting, traveling through the internet. Yes, quite fascinating. Okay, let's go back to reality now, because this is real stuff, everyone. So, we can ask and answer the following questions from our business systems, from our products that we are developing right now. What's my current state? What's my current environment? And what's my current configuration? Is this the most optimal state I can be in? Is this the most optimal configuration? Also, how can I recover from this fault and prevent it in the future? How can I avoid this threat and prevent it in the future? I want these disasters to stop happening. How do I respond to an unexpected condition? Autonomic systems, AI-driven architecture, requires 3 ingredients. It requires first an observability mesh, what Neil Ford and I sometimes call a governance mesh, although I prefer the term observability mesh. It requires another ingredient, agentic AI. And it requires a third ingredient, reactive patterns of architecture. Now, let's take a look at each of these ingredients. Then you know what we're going to do? We're going to combine them together and actually see how to build autonomic systems in our applications today. The observability mesh allows us to continually, through observability, capture metrics, events, logs, and traces. This is formally known as MELT within the observability space and DevOps. I'm not really fond of the word or acronym MELT. It's easy to remember. MELT, metrics, events, logs, traces. However, I don't want this thing to melt. It kind of gives it like a sort of a negative connotation, doesn't it? We don't want our observability mesh to melt away. And so I'm kind of really advocating, let's move these things around. Can we call it TEML? A little bit better. Anyways, it's the ability to capture all of these artifacts from all aspects of our system and our environment to have the data. So in order to make decisions in an AI, we need data. That's the source of our data. Then we leverage the second ingredient, agentic AI. For example, and this is consisting of agents. I have an agent that is looking for a current configuration. Let's say this is some sort of setting, thread pool. And it says, well, the current setting's 300, but based on my knowledge from the observability mesh and learning, the optimal configuration is actually 260. And you know what it does? I'm going to show you how this is doing it in the next couple of minutes, but it changes the system. But then we have another agent in our agentic AI who's responsible for making sure that that response time is fully optimal. And it says, whoa, wait a minute, all of a sudden something just changed. The response time degraded from 600 to 800 milliseconds. What happened? You can see this will not work. Agentic AI is a necessary ingredient, but it has to be formed into an agentic mesh. These agents have to communicate with each other through various protocols because each agent has very specific learned knowledge about my area, but I don't know about your area or Vlad's area or Florian's area. So we have to communicate to say, look, I think 260 would be a good value here. Let's see, can we try it out? Whoa, no, that's not good. Let's revert it back. And we see a little blip in the system because we're all communicating. The third ingredient are reactive patterns of architecture. These allow us, these architectural patterns, which by the way do exist, I've been using them for over a decade. As a matter of fact, a decade and a half, to allow us to be self-configuring. The thread delegate pattern combined with the supervisor consumer pattern allows us, without human intervention, to be able to expand and grow our systems as our business grows. We couple that with configuration parameters or configuration patterns that automatically adjust those configurations. That's self-configuring. We combine it with self-healing patterns, the workflow event pattern, to programmatically fix errors as they occur, combined with the producer control flow pattern, which applies back pressure if I'm suddenly detecting that our downstream systems are in trouble. If I keep flooding it with data and processing, it's going to die. Back up a little bit, upstream systems. That's self-healing. And combine that with being self-aware. Things like the channel monitoring pattern or any other kind of patterns we use to detect our environment. Okay, so now let's create an autonomic system. We take our three ingredients, and I'm going to take our software architecture now. And with that software architecture, we apply and implement these reactive patterns of architecture in our code. Then we provide observability, all sorts of metrics about my environment to the observability mesh. Agentic AI comes in parallel to that observability mesh because that's its data, and correspondingly analyzes that through agents very specific to one part of our system and says, you need to change. And consequently, goes back to the architecture, and we apply that change. This is amazing stuff. This is AI-driven architecture. This is amazing stuff. So we look at these four key trends, but you see something very interesting and similar about these. First of all, architectural intersections. This key trend requires architecture as code to validate all of these intersections. Also, AI-driven architecture requires distributed architectures, and it also requires architecture as code to validate it. Folks, everyone, this is not the future of software architecture. This is software architecture now. Thank you all so much.